Testing, testing. Testing, testing.
Okay, mic works. Oh, it's streaming right now. It's getting all my testing. You can clip it later. It's fine. Presenter view. Yes. Okay. How do I go full screen? It's that button. But I want my notes, which are right here. But then it does, well, it does work, but then it does this. F11, I didn't do okay, function F11? There we go. Okay.
Make sure also before you, whenever you start talking about, you go to the Caesar components after.
Just mention at the beginning, we're going to go to Caesar.
Yeah, at the end, once this is done, we go over those, the answers, or the solutions.
Okay. All right. Is everyone settled in? All right, let's get started. So if you haven't signed in, please do that. Real quick, we've got a message from Take about Fire Talks.
So CSG encourages non-CSG students to make a presentation about any technical topics, right?
Anything security related.
Yeah, anything security related. So please sign up via this form and let me see your presentation. Thank you.
You can put it on your resume and stuff. It's fun. You'll enjoy it. All right. And quick note, at the end of this, we are going to go over CTF problems from the past 2 weeks. So if you attempted those, stick around and we'll tell you the solution. Right? Solution? Okay. Well, cool. Does that button work? Next. One next. Okay, so this is a talk over just the basics of cryptography. So I'm going to cover just a few fundamental topics, and then I'll pass it over to Zarish, who's going to cover some other stuff. So first thing I want to talk about is ciphers. So ciphers are a really old kind of cryptography because they are really easy to compute, both encoding and decoding. Usually they just involve shifting positions in a string or shifting the character value of a character. So a lot of people can just do this in their head because it's a fairly simple operation. The one you might have heard of, or you have probably seen in intro CTFs, is the Caesar cipher, where you will, if you have the string "Hello World," you're going to shift each character upwards or downwards in the alphabet by a constant value. So your H would become an M, and then H I J K L M, and your E would become F G H I J. And it would, it would look unintelligible to the, common reader. But if you're sending your message to someone who knows which number you're, encoding by, they can just negate your number, and then they can decode it pretty easy. It was named the Caesar cipher because Julius Caesar would use it a lot when he would write letters to people. So that's pretty interesting. But ciphers like this are very, very easy to crack because there's only so much you can do to encrypt a message. But they are the basis of more complicated things. So let's look at those. much more complicated things like symmetric encryption. So symmetric encryption is a class of encryption algorithms that describes algorithms that use a single key to both encrypt and decrypt. So the key here is kind of synonymous with the constant shift number that we used in the cipher. It's just some chunk of information that will tell the algorithm exactly how to convert one character into some other string of bits. There's the most common symmetric encryption scheme is probably AES. AES is on everything. Symmetric encryption is used usually to encrypt like data that's just sitting around that you don't want anyone to read, but you also want to be able to decrypt pretty easily. So like Google Drive encrypts all of your data with AES. And assuming that hackers who break into your Google Drive or break into the Google Drive backend, as long as they can't find the encryption key, there's essentially a 0% chance that your data is going to be decryptable, which is pretty nice. What's the question? So I can speak from experience on one little section. I don't know if this is how you really do it, on how the Google Drive engineers do it, but 2 summers ago I wrote a file system that would encrypt all of its contents, and it ended up splitting the AES encryption key into big chunks, and that was one way I did it. Was I split the key into multiple pieces. I spread them across on the drive. I spread them across multiple drives, and there's really nothing you can do to guarantee that an attacker won't find your key and use it or reconstruct your key however you hide it. It's just, the more you do to hide it, the better a chance there is that most hackers won't be able to construct your key and decrypt all of your information. So take that as you will, but the general answer is there's kind of nothing you can do to stop someone who really wants to hack you. Common theme. So the alternative to symmetric encryption is asymmetric encryption. And the big idea here is that, and another name is public key encryption, which you might have heard of. The difference here is that it uses 2 keys instead of 1. And one of them is a public key, one of them is a private key. The public keys are used to encrypt messages, so you can give those keys to anybody, and all they're going to be able to do is encrypt stuff, which anyone can do that already. So if you find someone's, SSH public key, you can't really do anything to them. However, private keys are used to decrypt messages that were encrypted with the public key. So if I give you my public key and you encrypt something and then send back the ciphertext to me, I'll be able to decrypt it no problem because I've got my own private key. So if you want to maintain secure communication with somebody, you have to keep your private keys private, right? If you've if you've set up an SSH key on your GitHub account so that you can, securely transfer data to GitHub and back, that's public key encryption. I forget which one do they use. Do they use RSA in the default example? ED5519 or something like that. That's asymmetric encryption, and you're basically you're putting your public key in the box. I'm pretty sure. I don't know. Doesn't really matter. But again, asymmetric encryption is just used to basically authenticate, especially when you're modifying data and then sending it to someone. So you can use it as a digital signature to prove that you sent this message or you didn't send this message or something like that. And then a third big tenet of cryptography is key exchange. So this diagram on the right is pretty famous. It describes the Diffie-Hellman key exchange algorithm, which is super, super useful, and you use it all the time without knowing it. key exchange algorithms, they utilize asymmetric encryption to help two parties basically create secrets together without leaking any information about those secrets to any attacker, as long as your mode of transport is secure. So one example, and this is what you use all the time, is SSL. So whenever you connect to a website and you see HTTPS, that's an SSL connection. And it utilizes the Diffie-Hellman key exchange algorithm to let the server and client basically build a symmetric encryption key together. And that way they both have their symmetric encryption key. Attackers don't know your symmetric encryption key. And then I can encrypt my requests, send them to the server. Well, the server's got the encryption key, so they can decrypt it, they can process, they can send back HTML and JavaScript and whatever, encrypt it, and then I can decrypt it on my end, and it all works, and it's beautiful. And we do not have a SSL certificate on our website, so we're not doing that right now, but we should be, but it's hard, so I think we get a break on that one. I don't know, SSL is really cool. I'd like to give a talk on that alone one day, because the handshake is just a really interesting topic. And the last thing I'm going to talk about for a little bit is pseudorandom number generation. So these are kind of like all over the place topics, but I wanted to cover a lot of bases. So random number generation is like super important to cryptography, because imagine you're using Diffie-Hellman to build your encryption keys. But if you don't have a proper random source when you're generating your asymmetric encryption keys, on the server side, for example, an attacker could predict what your key looks like, or maybe they could know for 100% what your key looks like. And then they can just reconstruct your private key on their own with no input from you, which is very bad. So that's why pseudorandom number generation is a big deal, and that's why there's so much research into it. But the basic idea is that you want to map some seed, a deterministic seed that they call the random seed, to a bit string, some sequence of bits, zeros and ones. And the goal is to match a normal distribution as closely as possible, because normal distributions pop up everywhere in nature. So if you can get your random number generator to look like that, you're basically, simulating the randomness of the universe and whatnot, which would be great. The issue is that true randomness is basically unattainable. Digital machines are more or less deterministic. To get random behavior, computers will often read, at least on Unix machines, dev-urandom. It's kind of a file. You can read data from it, and it will fill up this buffer with random data that comes from your mouse driver and your keyboard driver, because humans are pretty random. I might shake my mouse, a millimeter to the left and then a millimeter at a 73.5 degree angle, and all that data can be pulled straight from the device drivers and used to just create a bunch of random, hopefully random data. One story that people tell a lot is Cloudflare's random number generator is implemented with a camera pointing at a wall of lava lamps. And then they take a hash they hash the picture of the lava lamps, and that's like a fairly random seed, because lava lamps are pretty random. I couldn't predict which way the blobs would go. This image on the right here is the middle square method of random number generation. It was written by John von Neumann in 1949. He actually showed this at a conference as a bad example of pseudorandom number generation, because it does tend to repeat its sequences. So if you pull numbers from it over and over and over, you're guaranteed to start pulling the same numbers over and over. So you'll get into a loop, which is bad. But I mean, it's super simple, right? So a fair amount of number generation functions like this are much more complicated. So if you need something that's not super secure, but you want something that kind of looks random, maybe use the middle square method. Any questions? No. Well, I will pass it off to Zarish.
Okay, hi guys. So the first thing I'm going to be talking about is hashing. So hashing is obviously a great way to keep information secure, and there are different kind of algorithms that you can use. So there's the SHA-1 family, SHA-2, which contains SHA-256, which is a really big one that it's really popular, MD5. And basically what happens is you have an input, and then a hashing algorithm is going to be used, and it gives you a hashed output. Now, some of the key things that we look at whenever you're using a hashing algorithm to make sure it's actually good is, one, it should be computationally efficient. So the computer should actually be able to create the hash in a timely manner. It shouldn't take too long for it to do that. It should be deterministic, meaning that every time you hash a specific string, it should give you the same output. And then it should be pre-image resistant, meaning that the content shouldn't be revealed during this process. It should be collision resistant. So basically, if you have two different strings, you don't want it to map to the exact same hash value. And then it should be impossible to reverse engineer, because then why would you actually hash it? Because you don't want people to look at it. And an example of how hashing can be used is, let's say you have an account. You create an account and you put in your username, a password, and then let's say the database stores just your hash password, because if it gets hacked, you don't want your password stored as plain text. So when you log in again and you enter your credentials, the password will be hashed again, and it will be checked against the one that's already stored. So that's the way that hashing is actually verified. And next, oh, sorry.
If it's impossible to reverse engineer hashing, why there are multiple hashing algorithms?
Honestly, that's a good question. I'm gonna take a guess on that. I'm probably gonna say maybe because all of them don't exactly have the same features, or there's always probably improvements that happen. We know it's with computers changing and evolving, it's easier to crack a lot of the hashing and secure methods that we have. So just evolving with the computer and technology, that's my guess, honestly.
Also, there's like reverse databases for common hashes as well. So if you need a hash that's secure for shorter or small
Yeah.
things, then databases have those. So
Sure.
I guess you would need a new hash for that.
Yes, that's a good answer too. Thank you. And then next is RSA encryption. So RSA encryption uses asymmetric encryption to secure the messages, as Charles mentioned before. So this picture is kind of an example of what happens. In this case, we have Bob has his public key that Alice has, and Alice wants to send a certain content to Bob. So she's going to use his public key and then send it over back to him, and he'll decrypt it using his private key that only he has access to. And this helps with assuring CIA, so confidentiality, integrity, and availability. And RSA, because it's asymmetric, it's going to use a public key to encode the messages and then a private key to decode. So the public key is generated by, you'll get two random prime numbers generated. They're multiplied to get a large number, which is going to be used as the public key. And then the private key uses those two random generated prime numbers and does a different kind of math to it to get the private key. And the goal is, the logic behind using the prime numbers is that you want to get a really large integer so that it's hard to factor it. If it takes a long time for a human to actually factor that number, then a computer would also take a pretty long time to factor that number back into the two prime numbers. And currently, the size of the key that you would want to have for it to be a secure RSA encryption is going to be around 4,026 bits, which is about 1,234 digits. It used to be 1024, but over time, computers have been able to even decode those. So we're going for a bigger bit size. And then it's used in a lot of places like Secure Shell, SSL, TLS. So making sure there's a good secure web connection whenever you're on a website. You don't want to be stuck in like a man-in-the-middle attack. And then you see it a lot in password exchange, banking, online shopping. And yeah, that's why it's also so secure, because it's difficult to factor that key if it's a very large number outputted by prime numbers. And then, any questions? Okay. Back to Charles.
Right. So that's the big chunk of our presentation. I'm going to be talking about John the Ripper for a second, because that's going to help you with the CTF challenge. So John is a free and open source password cracking tool. Specifically, it's optimized for CPU use, which is really nice because not everyone has a big graphics card. It's nice because it can automatically detect the hash types of ciphertext, which is really cool. And then it can automatically try to unhash them for you. Or not necessarily unhash, but find text that hashes to the same ciphertext. One thing John does is it makes heavy use of word lists. So if you're not familiar, a word list is a plain text kind of dictionary of sequences that could be in the plain text. So if I am trying to crack the password of someone, give me a celebrity.
Donald Trump.
Give me a different celebrity. A non-controversial one. I heard one over here, but I don't know.
Mariah Carey.
Mariah Carey. I would probably make, if I wanted to crack Mariah Carey's password, I would probably put together a word list of Christmas-related things and music-related things, right? And assuming that she has bad password etiquette, I would be able to pretty easily crack her password by giving John her password hash and a word list. So it's going to try a bunch of permutations in the word list to see, did she stick these two words and then a number at the end, or did she replace the A's with at symbols or something like that? So that's what a word list is, and John is going to do most of the work for you there. On Linux or Unix machines, passwords are pretty much always stored hashed in a file called etsy-shadow. In combination with some user information in Etsy password. And so given the shadow file and the password file, John can pretty easily break that encryption in a small amount of time, unless the plaintext password is pretty complex. So that's interesting. And the last thing I want to say is that there are other tools to solve this problem. I suggested John the Ripper because, again, if you don't have a big GPU, this is like the one to use. Hashcat is really good, but it's exclusively GPU based, so you have to have OpenCL or something installed.
Hashcat is also on Windows, while John the Ripper is not. So if you're limited by platform, that's the one most people use.
There you go. That is all I've got. Are there any questions?
What would your techniques be for generating word lists for someone who is better at it?
So there exists word lists on the internet that people pass around, and I guess some are considered better than others. I wouldn't say password cracking is something that I've done a lot of work in, so I don't want to give you any incorrect information, but I think I'm pretty sure if my hacker lore is correct, word lists are kind of like hush-hush, like you don't want to share them around because people put effort into making good word lists that are better than the average one you can find on Google. So I don't know. I think you'd have to look into that on your own to find a good answer.
Do some digging. RockU is the big one that everyone knows. Like if
Yeah.
you're doing a CTF challenge, you try RockU first. Besides that, there are some public GitHub repositories where people share or collect password lists. Granted, they're not going to be the best password lists, but it's more passwords to try than what RockU gives you.
Mm. one slide back.
Chase Bank are you tracking again? Say
Cool. Do we want to stream the answers to the CTF? No. Okay. Bye.